Okay, thank you. Yeah, so the dimension 1 is kind of main, kind of basic playground for all the theory, and I will explain various aspects of Riemann-Hilbert correspondence, and which could be probably useful for Jan Söbelman talk. So first of all, if we have, if X is a complex curve, the situation is very simple. We have a cotangent bundle to X, and any conical Lagrangian complex subvarieties should be any conical complex Lagrangian subset, algebraic. It could be only a zero section, or we take maybe several union of cotangent fibers where X belongs to some finite set. Yeah, so that's pretty easy situation. And if we're interested in holonomic D modules whose characteristic variety belongs to this set, if M is holonomic D module, then we see that it will be and I don't say it's what's important, it's not necessarily regular. So the essence of my talk is irregularity of holonomic D modules. So what we see it then M on X minus this finite set is algebraic vector bundle. Let's say it's algebraic curve. Bundle with connection. Automatically in dimension 1 connection is flat. And then you get some contribution for singular points, when, which we'll discuss later. Yeah, so if you want to understand Riemann-Hilbert correspondence, first one should kind of understand it locally. And let's consider the case of, go from algebraic to analytic, go to the case of punctured disk. Which is maybe punctured to denote by star, a set of complex numbers that at absolute value of z is less than 1, and disk will be open disk. And we can be interested in the following thing. We have a holomorphic vector bundle on punctured disk with connection nabla and with meromorphic structure at 0. At z equals 0. What does it mean, meromorphic structure? It means that we choose an equivalence class of trivializations of holomorphic trivializations of bundle E. Model is a group of maps from D star to GL RC. R is the rank of my bundle, which are meromorphic at 0, which has only finite order poles of 0. So I get map G such that both G and G inverse have all matrix coefficients of matrices G and G inverse have finite order pole. No, I have a map. I have a linear map. I get matrix valued functions. And I want to ask that all matrix coefficients of, have essentially, it's maybe enough for one of them. Yeah, have finite order pole at z goes to 0. Yeah, and a connection also has, in this trivialization, has also finite order pole. Yeah. Without meromorphic structure, so the small remark. If we forget, kind of without meromorphic structure, classification is obvious. It's the only invariant to get a monodromy. If we forget about meromorphic structure, then we get the same as local systems of finite dimensional vectors, complex vector spaces, finite dimensional spaces, complex spaces over disk, the same as representation of fundamental group, or kind of representations of fundamental group, which is Z in finite dimensional spaces. And I will say it's kind of really funny way. Another way to say what is this category, it will be the same as coherent shifts on C star with finite support. It will be, the support will be eigenvalues of monodromy, and this group ring is a fundamental group. Is Laurent polynomials maybe in some one variable. And if you consider finite dimensional representation, you get this is finite, coherent shifts, which has global sections, just finite dimensional space. Okay, so now what meromorphic structure adds to the story? So I will describe Riemann-Hilbert correspondence in this case. So the first, you consider formal completion. Yeah, so we introduce instead of disk, we consider formal punctured disks, and algebraically described by a field which is known by K, which is a field of Laurent series. So I consider set of all series where an are complex numbers, but there's no convergence condition at all. Yeah, so that's a field, and it contains a ring of integers, which is C of Z. Yeah, so it means that here n rate is 0. And if I translate algebraically what I'm looking for, now E formal, whatever I just denoted by same E, will be finite dimensional K module of rank K R, which is R is the same kind of A is isomorphic to K to R, endowed with connection. Again, having first order pole, which can be set, can be formulated as the following: A is a module, E is in fact this module over some kind of formal differential operators on the punctured disk, which is by definition, I consider polynomials in kind of dz. In dz, where dz is not commuting, it's a kind of set of finite expressions, sum over f 0 to n for some n, fk dz to k, fk belongs to this. And we use, so it's kind of twisted polynomials in one variable. This is derivation. Okay, so it's a module of a kind of analog of ring of appropriate ring of differential operators, which is finite dimensional over scalars. Yeah. So I'll give some definition, which this E delta is regular. If the following holds, that operator, if there exists E0 in E, which what's called lattice. So E0 is OK module. In fact, free of rank of the same rank, such that E0, if we change scalar, we get E. So, and also E0, and the main axiom that E0 is stable under this Euler differential operator. That's a definition of regular. And I'll just maybe want to give you an idea of how proofs in this theory goes on. Let's classify this regular formal D modules. The answer will be exactly classification of these D modules without holomorphicity condition, meromorphicity condition. So let's try to classify these regular D modules. The story is the following. If we have this E0, then E0 contains Z0, contains E square E0, and so on. You get infinite chain of subspaces of finite codimension. And if you get quotients, just by multiplication by Z, you can identify all quotients. And all just isomorphic to CR. It's clear, so you get a, and then E0, it's kind of equal to projective limit of finite dimensional spaces. Yeah, over some n. E0 divided by, which are finite dimensional. Now one can try to look on this operator Z. We have that Z dz E0 contains an E0, and then by Leibniz rule, it implies that Z dz Z for any whatever n E0 contains Z to power n E0. So this operator Z or dz preserves the filtration. Preserves the filtration. And so you get some Z dz acts on subsequent quotients. So you get operator acting on finite dimensional spaces. Then it has a a certain spectrum, or it can be thought as this coherent shifts on you get some certain spectrum. But spectrum, it's element on subset on C, not of C star. And now, if you consider corresponding eigenvalues here, you add 1. Yeah, so what you get certain subspace, subset, whatever, S0, and you get certain subset S in C. Then you get subset S plus 1, S plus 2, and so on. Now, and by the way, if you consider spectrum on kind of finite extension, it will be union of spectra. And what you can conclude, that operator ZDZ has eigenvectors and maybe associated n plus associated eigenvectors when you have Jordan blocks, associated vectors. In the whole E0. Yeah, so you get this picture, and one can try to look on this E0. We have action of operator Z and ZDZ, which here maybe I denote by something like lambda. And this Z, so we kind of change our point of view. We look E0, it's module over polynomials of lambda. And operator multiplication by Z will be operator which said that its modules equivalent with respect to shift of, or equivalent kind of on one side when shift lambda by 1. So what happens here? We get some certain subset S. Then we consider subset S shifted by 1. Which they can overlap and shifted by 2 and so on. We kind of consider a union of all shifts, integers S plus n, will be support of A0 as, or yeah, of the set of it will be support of some infinite rank C of lambda module, consisting of finite linear vectors which are finite with respect to of C lambda finite vectors in E. So vectors which are said that this thing generate finite dimensional space. Yeah. Yes. So this when we go to projective limit, we get huge space, but the claim it contains a certain nice countable dimensional space. Namely, you try to leave these two eigenvectors in this, or associated eigenvectors in the whole space. So what together you get? You get certain subset, kind of S plus Z greater than 0, which is infinite semi-invariant by the shift by. in E0, yeah, in E0, yeah. Yeah, so it's certain thing which depends on choice of E0. And you get kind of coherent shift with support on this finite union on arithmetic progressions with step 1. And covariant respect to shift by 1. And if you extend, you can also extend it formally to the left. You replace E0 by whole E. So you can extend it to the left as well. And because we can, our ring E on Z is invertible, one can multiply by negative power of E. And what one get kind of quasi-coherent sheaf, because it's infinite on a fine line, invariant under shift by integers, and with the following property. One can choose a fundamental domain of this sheaf of integers. We consider a set of lambdas, where real part of lambda is from, let's say, from semi-interval. It's any fundamental domain. And here we get some kind of finite support with some multiplicities. And one can say that one gets just coherent sheaf in the fundamental domain with zero-dimensional support. And you repeat it infinitely many times by shifts. So that will be the description of this regular D-module. And then if one apply exponential map, take its he'll get fundamental domain of C of Z, and then you apply exponential map, call this capital T. You get invertible, you get on C star, we get coherent sheaf with zero-dimensional support. So that's basic case how we classify regular holonomic D-module over informal case. Now, and we see it's the same as local system on a circle. The claim is that there are many more, even formal case, D-module kind of bundles with connection which are not regular, and there was a famous level Turretin theorem which classifies them, and let me formulate it in the following way. First, I consider possible irregular terms. Definition, the set of irregular terms, it's the following thing. If you consider Galo, K bar, OK orbits, formulate this formula, but then explain what does it mean. In K bar over K bar. What is K bar? K bar, it's algebraic closure of K. And it's union over all, let's say, D greater than 1. You consider Lorentz series informal D's power of this variable z. It's called the field of Puiseux series. Then what is the Galois group of k bar OK? Is actually pro-finite completion of the group of integers, and generator acts in the following way. So if for any d, it maps to exponent of 2 pi I over d, d to the power 1 over d. Yeah, that's the action of the generator. And when we consider k prime over ak prime, it's a quotient just of abelian groups. It will be just a set of finite sums of whatever z to power lambda, where lambda is rational number and strictly less than 0, because zero positive numbers will belong to the ring of integer. And then the quotient get only finite linear combination. Yeah, so you get some kind of some kind of set of sum over whatever c i's x to power lambda I, where c I and c and lambda I are rational numbers and strictly negative. And then a Galois group acts here with finitely many orbits. You multiply by exponent of 2 pi I over kind of the largest, what's called least common multiple of denominators of all lambda I. It could be 1 or 2, whatever. So you get some finitely many orbits, and the theorem can be said the following. Let's consider abelian category of, one can say, holonomic d modules of this ring, which is the same as, in this case, as vector bundles of holonomic d of kind of formal of the puncture disk modules, the same as connections, bundles with connections on what I talk right now, is canonically isomorphic to direct sum over all irregular terms of categories which we just discussed. Finite dimensional representation of local finite of category of finite dimensional representations of Z, or the same as coherent sheaves with zero-dimensional support on C star. Yeah. This is here it doesn't matter. No, coherent with finite, with compact, finite, zero-dimensional support on C star. Yeah. And in fact, for each irregular term will be certain topological circle such that it will be local systems on a circle, or local system on. So how how one can. So, so the exact description is the following. Yeah. If all lambda I belongs to Z, so the Galois group, it's kind of fixed point of Galois group. Then this corresponding block, yeah, this is called decomposition of blocks because there are different subcategories do not talk to each other. There's no X, no coms. They're completely independent. So this corresponding block is the following. It's regular module tensoring by K and okay by exponent of this sometimes okay. This is bundle. This gives a bundle with this connection. You formally differentiate it, and you get rank 1 bundle, and you multiply by a local regular D modules. Lambda I, yeah, lambda I integers, yeah. It will be negative integers. And by the way, regular D modules can be, in this case, are the same as you consider direct sum of copies. What you do, get x to power lambda, maybe x to power time lambda log x. Wait a second. It will be direct sum of some finite set of lambda in C with in our fundamental domain, and corresponding kind of indecomposable modules will be the following. You consider maybe how to say. Or maybe just say in a different way, kind of indecomposable regular D modules are of the following type. You consider x to power lambda times k plus x to power lambda log x times k up to certain you consider this direct sums, and it's closed under multiplication by x and derivations. And then you can normalize, let's say, real lambdas between 0 and 1. This will be the total list of all indecomposable modules. Now you can multiply by such guys. It will be another indecomposable models. And if lambdas has some, if Galois group X with some orbit of certain, if orbit is via some quotient, a certain whatever n z, where n will be least common multiple of the story, then what will happen? This Puiseux series will be Laurent polynomial with negative powers. You get consider nth root of z. You get on w. You consider variable w, which is nth root of z. You do the same story in variable w, And then consider push forward. You consider what good? Consider regular D module in W. Multiplied by exp. Again, certain some let's call it Ci, Wi, I are negative integers, and taking push forward, it means that we consider the same module, but only over Laurent series in Z. As which is subrincan differential operators in W. Yeah, so it's so that's a complete list of all modules. Now, why? How to see it? I just want to indicate the proof of the theorem and what is the geometric meaning of all the regular terms. So if M is a D module, kind of this formal D module, then it contains this maximal regular part, which eventually should correspond to contribution of 0 regular term. In this case, it will be kind of regular part and this irregular part. And a regular part is it's the following. It's kind of K subspace generated by ZdZ finite vectors. Because in regular modules there are plenty of ZdZ finite vectors, and they generate the whole part. And what is M irregular? It is second. On M irregular can be formalized in the following way, that if consider operator Z with dz, acting on a vector belongs to M irregular, if and only if the following happens. When I consider Z with dz, it acts kind of topologically nilpotent on M. So this on vector V, if consider, maybe I'm slightly checking, if consider this big powers of 0 dz, it goes to 0 for n greater than 0. And in fact, we can say that so let's explain basic geometry behind this level 2 routine decomposition. One should do the following picture. Let's consider let's consider two variables, y and z, with Poisson bracket yz is equal to z. It will be Poisson bracket. Now y we consider as kind of very small, and eventually we can say it's y will be formal variable, but z it will be not small, and z belongs to C, which sits in CP1. So what we should really consider is we consider a formal neighborhood of CP1 cross 0 in CP1, or maybe 0 cross CP1 in C cross CP1 is variable z and w, z and y. So we have such kind of formal variety with Poisson bracket. And Poisson bracket can be written as kind of vector by vector field. And if we make inverse, we get the inverse dy dz. And you get two form which has pole of order 1 along one divisor and pole of order 2 along second divisor. And we consider only formal neighborhood of this P1. What is the meaning of this irregular set of irregular terms? I want to explain some geometric origin of this. Namely, so the theorem is the following. Oh, maybe not if I find the theorem, I'll just explain one basic story about Poisson structures on the surfaces. Suppose we get two integers, and suppose I get two form on C2, which has pole of order A in one on one curve and pole of order B in another curve. This pole of order A along one curve, along the curve, and of order B along some transversal curve. And we are looking near point of the intersection. Yeah, so then if you make a blow up, first of all, suppose A, B are greater than 1. If we make a blow up of intersection point, then the order of pole at the intersection point will be minus A plus B. It's easy calculation. Yeah. On a new divisor, order of pole is A plus B. And yeah, it's completely formal calculation, but in particular, one can go to the case when this guy is equal to 0. Sorry, it's A plus B minus 1. It's what's a really important story. Yeah, for example, if here you get pole for the 1, it will be like logarithmic singularities, and blow up again, get pole for the 1. And also, one can apply to the case where, let's say, B is equal to 0. If you get pole of order A, you get smooth point, then you can make it blow up. And then you get order of pole, it will be 1 less. And now one can do the following. In my picture, I have 2 divisors and have 1 intersection point. Now I start to make blow up of this intersection point. And the rule of the game, I want always to have on all new divisors want to have poles of order at least 1. So I can make some certain tree. For example, if I do it blow up once, I get again pole of order 2. Then I blow twice, I get pole of order 3. Then from this curve on pole for the 3, I get again get pole for the 2. Then I get again blow up at some point. I get again divisor pole for the 1. Yeah, so at some point I can get some divisors when I get logarithmic poles. And the theorem, it's the theorem that irregular terms are exactly the set of all divisors on blow-ups, on all possible blow-ups, where form has pole of order 1. Yeah, so it's kind of simple algebraic statement that you do this Puiseux series or you do this blow-ups. It's the same game, and let me explain why. The reason is the following. If you have if you get a regular term, yeah, which we can write something like sum of Ci Z2 minus I over n, where I belong to something, yeah, and GCD of all I is 1. Yeah, we can write irregular term and this finite linear combination. Yeah, so and assume that it's not 0. Let's call it, I don't know, something like 5z, multivalued function of z. Then we write, draw a curve. Namely vertical coordinate will be z dz of phi. Okay. We just formally draw a curve. We get some curve which projects to the base with some branches, and that curve, if it's non-zero, goes to this intersection point, which I have at infinity. A regular term corresponds to curves which intersect vertical divisor. Yeah, so we get a curve. So we get a kind of germ of analytic curve or formal curve which goes to intersection. And now we can do the following, do our game. If the curve goes to intersection of 2 divisors, we make a blow up. And then it's again goes somewhere. And if it again goes to intersection, we again blow up, and eventually it will not go to intersection of divisor, it will go to divisor itself. when it goes to divisor itself, if it has order of pole greater than 1, we again make blow up. Then we get the same. We can repeat the situation from the very beginning. Can go to intersection and so on, but eventually the process will stop, and eventually this curve will go to divisor. We get order of pole equal to exactly 1, and here we stop. Yeah. So any curve gives this canonical divisor. Yeah. So it's kind of complicated tree when we have to start induction over, but that's a construction. How from a regular term we go to these divisors, and the same story can be repeated for D modules. Why from these D modules you see regular terms? It can be repeated in the following way. When we have a D module. When we have a D module, it's modulo of a non-commutative algebra, but if you kind of imagine the algebra will be commutative, it looks like it's a model over functions on some sheaf with one-dimensional support on this in this surface. Yeah. So if you kind of imagine. We have this D module. Can be thought. Oh, just stop to draw. D module looks like the following. One can imagine the picture like this. That suppose we get several curves. Some pieces go to inner point. Yeah, let's make kind of cartoon picture. Consider coherent shifts on these formal schemes, which one consider coherent shifts. On this formal neighborhood, maybe here consider coherent shifts on it with minus. Yeah, so we do something which is from which it's not really good language algebra geometry. For formal schemes, I can remove actual P1, and then it will have no points. It's like Lorentz series minus. 0 CP1. Consider coherent shifts on these things minus things with purely one-dimensional support. So you can imagine that you get kind of finitely many curves and or maybe thickening curves and vector bundles on the thickening curves. Then you can extend not uniquely to shifts on with support on shifts on the whole formal neighborhood without removed zero fiber. So you can, so it means that you can choose certain M0 and M0 will be OK module, kind of lattice, and satisfying, according to this picture, the following property. It will be sum of regular irregular parts, where on regular part and M0 will be M0 regular plus M0 irregular. This will correspond to M0 irregular, and the rest correspond to M0 regular. And then one can read what are properties, algebraic properties of M0 irregular and regular will be the following. On M0 regular, sorry, M0. No, and then if you make tensor product, that will get, yeah, but will be some kind of notion of natural lattice for a regular part. Here we get 0 dz acts has kind of topological the kind of dense subset of finite vectors. And what happens here, you see that it will be model of a formal power series, like model formal power series of two variables. M0 regular will be model of a formal power series in variable z and z dz inverse, which will be a coordinate near the things. Yeah, so so that's it. It's the differential regular part. So consider on M0 this operator will be invertible, and moreover, if you consider multiply by powers of z and big powers of this inverse of this operator, you go to 0. It will be converged. So to get formal power series in two non-commutative variables. And now I can repeat the situation with blow up. So the claim that on this scheme on P1, we have a sheaf in just in the Zariski topology of non-commutative algebras. Quantizing this Poisson bracket. Because the commutator is vanished on the thing, so we can make formal completion. And we have our module will be with this choice of this lattice M0 will become a complex of modules of the complex sheaf of modules of the non-commutative ring. But there's no small parameter. Yeah, there's no h bar parameter because its Poisson bracket vanishes exactly on this story. And then if you do blow up with this Poisson manifold on this new, it will be formal neighborhood of a chain of some kind of tree. We get some formal neighborhood of a kind of more complicated, some chain of P1. And on these things, you get, again, sheaf of non-commutative algebras. And the same picture which you have in commutative situation, you can repeat in non-commutative case, and then you see that your module eventually will produce something which, when you meet something, when support intersecticon, when you restrict this module over this chain of P1, it will be usual coherent shift. It will be zero-dimensional coherent shift, sitting supported only in some points on some divisors when we had poles of order 1. Yeah, so it's essentially what here goes on. One can introduce certain kind of for any AB greater than 1. One can consider certain non-commutative ring. Namely, you have two variables, x1, x2. Can consider we take Poisson bracket of this form, and you quantize this algebra. So you consider so it's a get kind of quantization of form power series in think of two variables. For example, here for numbers 1 and 2, one gets this bizarre ring of form power this differential operators with some negative powers, and then one can make blow up from DAB and get P1, and here the completion will be DAA plus B plus 1. One can make like if you forget about non-commutativity, you can make from module if you get coherent shift on support on a curve which goes to intersection, you can make blow up and get coherent shift. Yes, yes, yeah. Yeah, it will get non-affine, yeah. Yeah, but we already started with non-affine because it's already have P1. Yeah. Now, so that using this, I think it's actually the right way to understand level 2 retain theorem, because I don't know, naively I thought before that, okay, exponents are basic things and multiply by exponents, but it's kind of formal algebraic expression. And here that's geometric explanation of all this story. And one can do two things. For example, can consider the global case when we get x as a curve. Let's say the compact curve over complex numbers. Then one do the following. We consider cotangent bundle and compactify by adding copy of x at infinity. So get something projected to x. And here my two form, symplectic two form, will have pole of order 2 only. And now start to make blow-ups as I explained. You start, there's no second divisor, just blow up at any point. Start to make blow-ups. So first you choose a point on x, make blow-up, you get at new divisors pole for the 1, and then it will be really essentially our picture. And now we start to make here additional blow-ups and so on. And you get union of points of x of irregular terms at point x will be global R of C, will be the set of all divisors on all possible blow-ups where omega has logarithmic pole. Yeah, and that's intrinsic meaning. And you see that it's something intrinsically related to T star x, but not x itself. We consider symplectic manifold, consider all possible kind of divisors to infinity we can add where form has logarithmic pole. Now, in particular, if x is a fine line, so kind of x contains, just a second. That I explained you for compact curve, but the same can do for non-compact curve. And the things are, if it's a non-compact curve, one should do the following. You consider x, you compactify x by adding some point x0. You compactify, you make a blow-up, get pole of order 1, but now this vertical fiber became -1 curve, we can contract it. So you can contract, you can always, at punctures, you can replace by maybe logarithmic tangent bundle, so you get this already -1 divisors at punctures. And this will be canonical set associated with a non-compact curve, in particular if you get a non-compact curve which is A1, then there's a huge group of polynomial, it's very simple still, symplectomorphisms of C2, and it acts on this irregular term. So it's intrinsically a symplectic notion not related to the projection to X. And that's and then if you have D module, maybe a non-compact curve holonomic D module, you can associate a finite collection of regular terms with multiplicities. Yeah, okay, that's yeah, but it's kind of formal algebraic game, but in this case you don't get full description of category D models because of Stokes phenomena. And this is things which I want to talk about Stokes filtrations. Again, one can just do its case of puncture disk. Now it will be not formal. Yeah. So the by this level theorem, M will be connection with meromorphic at zero singularity, and we interesting up to meromorphic transformations. First, we can go to form of our series. You can see the M formal is direct sum over all of some finite collection of irregular terms of corresponding contributions of whatever M alpha. And this M alpha, I remind you, it looks like it was looking alpha. We can represent by some element in this K bar of K bar, and we can see the orbits by Galois. But let's choose representative of up to Galois group. It's some Puisop series in fractional powers. Get a finite linear combination of negative integer powers. And we write this thing as exponent times regular model in maybe fractional inverse powers of z. So yeah, it's so you can classify it in form of power series, but cannot do it globally. But still, the fact is, in a neighborhood, if you consider any sector, I think it's just sufficiently narrow sector, a neighborhood for any sufficiently narrow sector. And so narrow, I think it's maybe the size should be less than 1 over n over circle. On this sector, your equation one can identify with the formal normal form. This transformation which has only polynomial growth at 0 up to normal form. And the and this by transformation which are things which are O to up to z to O1, going on polynomial inside the sector. And then one can do the following. And for any consider direction in my plane, then or maybe just denote this things AG, you get a lot of functions. Then whatever it will be n of z, you get y alpha n will be different branches of my Lorentz Puiseux series, and you get finitely many branches, and you get various functions. They have for generic angle theta, they have all different growths as z equal to r is theta, r goes to 0, and theta is fixed. Because the growth of, yeah, for example, take something like exponent of square root of 1 or square root of z, exponent whatever, minus square root of, yeah, that's a typical behavior. You can have kind of two branches of exponent 1 root of z, and for generic theta, if you consider real part of 1 over square root of z and real part of minus square root of z, they will explain, all these things will be expanded as now some kind of all this expression as function of radius will be finite sum of rational powers of radius with real coefficients. And then if you have two such expressions, if they do not coincide, then this will be first leading term where they do not coincide, and one will dominate each other. And so that's so they have over different growths, you get kind of partially complete order on the set of branches. And in general, and if you rotate theta, this order will change for finitely many angles, and one can draw the following figure. One put along this ray points in an order corresponding to this different order of solutions. So this will be the fastest, this smallest, and it will be the largest solution corresponding to and then the order changes. So this is not terribly canonical procedure how to draw this order. So one get the following picture. Yeah, kind of. Yeah, what I claim is that what you do the same. It's just will be the following. You just draw several curves surrounding 0. Now, for example, one can again, one can do the following. One fix some epsilon very, very small, and draw curves which looks, the formula looks horrible, which is the following. Consider curve, replace theta by z, r, and consider exponent I theta multiplied by exponent of real part of my function alpha j is one of branches of my series applied to exponent of I theta times epsilon. Yeah, so it's a pretty ugly formula with double exponent, which gives you and take let epsilon be small and small. It will be eventually kind of stabilize to some picture. And or if we get such a curve, then one can consider the following question. One has for each ray, maybe one can make the following first additive category. Objects will be local systems on maybe C star, say, which is homotopy equivalent to S1, which we can try to think it's a local system outside of this picture, which is homotopy equivalent to component, connected component at infinity of C minus this collection of curves. So outside we get a local system. And now for each ray we get a filtration. Increasing filtration which start from 0. So maybe I'll say the following. So what we draw, we get maybe a collection of curves. Curves sitting in C star, sitting in C. And connection of curves, I don't know, kind of, let's call it C. And we co-orient them outwards. And consider kind of positive conormal bundle. This is a collection of curve. And outwards. Yeah, the oriented outwards. And now we consider constructible sheaves. On C with sheaves whatever F, such that singular support of this sheaf belongs to 0 section union of this positively varied conormal bundle, positive conormal bundle. And set and plus one condition that if stock at 0 is 0. And this structure of a bunch of filtrations on my of how solution grow by the growth. Yeah, we have what I want to say is that if you consider identify this formal model, it's uniquely defined up to some upper triangular. It's not uniquely defined. It's defined by automorphism in the sector. But at least the subset of solutions which grows very, very fast, or sections which decay very fast, it doesn't depend on like one exponent or another exponent. It's well-defined filtration. So we get a bunch of filtration satisfying some axiomatics. And the claim that you get exactly a category of sheaf with this macro-local support and with also this vanishing condition. So let me explain what is going on. If you get on a plane, you get co-oriented line, smooth curve first. What will, how we describe constructible shifts? First, it will be not even complex shift; it will be actual constructible shift. As a constructible shift, with if its singular support belongs to zero section union this positive conormal bundle, which means the following. First of all, the shift should be constructible with respect to this stratification, because we can also make negative constructive bundle. And when it's constructible in this stratification, we get fiber F0, F minus, and we get three essentially fibers, or if you locally, or fiber generic point of my curve, and a little bit on the left, a little bit on the right. And the structure of a shift is given by just two specialization or genification maps. From Stock at this point, we can go to Stock on the left and Stock on the right. And the fact it's this single supports contains only positive part means that this thing is isomorphism. And so we have a map from F minus to F plus, because F minus is equal to F0 and F0 maps to F plus. And yeah, so it means that if you get this picture, you kind of start to draw this picture. You put some maybe points inside my domains, and you get a map. You get certain quiver. If you get a map from this point, from F minus to F plus. Now one can analyze what goes on if you get intersection of two curves. Yeah, this should be a tensor product of equations in kind of one-dimensional equation. And what happens is the following. You get maybe F minus minus, F maybe plus minus, F minus plus, F plus plus. You get four spaces and four maps. And this diagram is commutative. It's a commutative diagram. But also you get extra condition when it just as if you read the definition of singular support, it gives you this extra condition, namely F minus maps to F minus plus F plus minus plus F plus plus is exact short exact sequence. Now, so yeah, and so get this elementary description of what are constructible shifts with micro-local support, and should start with 0 here. You get, and then all these maps will be embedding. You get just you get some subspace in each domain, but outside it could be not one vector space because it should be local system, depends on direction. Yeah, so that's a description of the Stokes data in terms of linear algebra, as Misha also wanted in other situation. And then we should repeat at any singular point. It gives a description of what are vector bundles with Markov connection on a surface. Yeah, that doesn't give you full Riemann-Hilbert correspondence in general because we consider only vector bundles. We don't have. I recall you that if you consider holonomic d-modules, it also can have kind of delta function contributions. That's a little bit non-trivial in terms of abelian categories, but one can prove the following result. Which is the following. Suppose X is a complex algebraic curve. Let's say it'll be compact, for simplicity, complex algebraic curve. And then we consider holonomic d-modules with given irregular terms. So we just find a set of points when we get singularities and maybe zero irregular terms and irregular singularities, and consider corresponding dB of this category. Bounded derived category will be a bounded derived category of constructible sheaves on surface. Set at micro-local support. Not micro-local support. Singular support lies in the union of kind of positive conormal bundle to the Stokes curves. In fact, Stokes was first who drew these curves in certain in his. I don't know exactly this parameterization, but at least in his Philip Bolch found in his text that he really drove, like for area equation, he drove some corresponding gadget. And here I drop this condition that this Stokes here is 0. Yeah, and this is exactly at delta function. It's kind of some little addition to this whatever the Riemann-Hilbert description for puncture disk. One can also add delta function, and to get this nice correspondence. The only trouble here is that when you draw this curve, it depends on parameter epsilon, and maybe depends on choice of local coordinate. So it's not exactly unique. If you choose different local coordinates, these curves move a little bit, but the whole category doesn't change. Actually, it's an example of this Guillemot-Kashivara-Shapira result. Then if you consider category of sheaves with some single condition of singular support, and which should be some subset or conical subset of a cotangent bundle, and we consider kind of contactomorphism at infinity of the contact boundary, then the category will stay the same. So what is real picture here is this, if you take kind of union of what we get here some non-compact conical R-conical singular Lagrangian subset in cotangent bundle to the curve, which will be 0 section, and union of kind of tubes over all my curves. Yeah, so we get this story, and there is another formulation, but I don't have time to say that. This is a language of constructible sheaves is a convenient language to describe of what's called local wrapped Foucault category for the singular Lagrangian set. Yeah, so this general perspective on which probably Jan will talk in more, that Riemann-Hilbert correspondence is equivalence between kind of some holonomic D-models will fix irregular parts, and object of Foucault category correspond to some kind of non-compact, roughly supported on this non-compact singular Lagrangian gadgets. Yeah, and maybe I'll finish with one nice example. I will just leave you an exercise. So Misha talked about various viewpoints on one basic category, abelian category. We consider perverse shifts on disk with a point. Yeah, you consider disk and a point and consider perverse shifts. The claim it's equivalent to the following picture. It's still another picture. You consider two ellipses oriented now inwards, and such that shift is equal to 0 outside, but now anything inside. You repeat, you start with the question, what is a linear algebra question? Eventually you lead to the question of the following form. You should find kind of two vector spaces. One will be associated greater than one circle, and here another circle, and maybe two operators, A and B, so that this metric is invertible. It's kind of in V1 plus V2. Direct sum of, this operator in direct sum of two vector spaces when this metric is invertible. It's exactly equivalent to this 5 psi and 1 minus AB. Yeah, it's exactly equivalent to this 1 minus NB invertible and 1 minus BA is invertible. And it's still another description which comes from this game, and yeah, but it's related to a story which I didn't have time to explain. This conjectural picture how these curves and these categories associated with shifts with given singular support can give a description of D-modules in deformation quantization sense when you get when the limit when h bar goes to 0 will be singular curve. If we get a singular curve in cotangent bundle, then consider maybe let's me just write it's holomorphic curve, maybe singular. It's kind of complex Lagrangian submanifold in cotangent bundle, and interesting in shift deformation quantization supports on this L. Is the question is pretty obvious. It's smooth point of L, but what happens in singular point? It's pretty not yet understood completely story, even in case of one dimension. But we have a conjectural answer related to that. If you get intersection points, you also get branch of maybe multi-valued function, take the same curves here and make the category, but arrange the 6 inwards, not outwards. And in particular, the case of just normal intersection of two branches, you get just the same guy. Yeah. Okay. Thank you.